All right, folks. Today we're going to talk about the exponential parent function, which I mentioned was kind of a review, but now we know more, and so we can talk more about it. So the exponential parent function starts out with f of x. And it's a little odd in the sense that the right part of the equation doesn't have any numbers in it. It is all variables. So the exponential parent function is f of x equals b to the power of x. Remember, in an exponential function, x is the exponent, hence the name exponential. So some things about the b. The b value is the base. These are, again, things from last year. B value is the base. The b value cannot be negative, so it needs to be greater than 0. And the other stipulation is that b is not 1. Because if you think about b being 1, a base of 1, if you raise 1 to any exponent, what is your answer always going to be? 1. And that means that all of your points are going to be an x value, comma, 1. And you're just going to have, yeah. If b equals 0, 0 raised to any exponent is what? 0. So can b be 0? No, because it's not going to give you the shape of the exponential function that we're looking for. Well, then there we go. That's right. It doesn't have to be greater than 1. It just has to be greater than 0 and not 1. So it could be like a half. It could be a fraction. It could be 0.25. And we're going to see in the next set of notes some examples of when b is between 0 and 1 and when it's just greater than 1. That's going to bring back thoughts about exponential growth and decay from last year. Do you remember talking about growth and decay? Maybe a little? Okay, so yeah, b can be between 0 and 1, or it could be greater than 1. It just can't be 1, and it can't be negative. So I'm going to move to my table because this is how we're going to generate the graph. The x values are all listed there for you, but we need a base in order to apply the x values as the exponent. So we're going to pick a base. I'm not going to pick 1 because I can't. 2 would be the better answer. So we're going to try when the base is 2. Yes, please. Try base equals 2. So we're going to take 2 and we're going to raise it to each x value as an exponent. And I'm actually going to start down here because it's going to look a little bit nicer. So my base is 2, right? 2 to the power of x. What is x here? 3. So 2 to the power of 3 is what? 8. So I'm going to go plot the point 3, 8 on my graph. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8. Come on, pen. No? There we go. Okay, not too bad, right? Yeah. If I go to an x value of 2, what is the base? 2 again. What is the exponent? 2. 2 squared is 4. So I'm going to go plot the point 2, 4. 1, 2, 1, 2, 3, 4. Oh, you're about to see if it's a parabola. Okay. What about the next one? What's the base? 2. It's always 2. That's what we're trying, is a base of 2. Raising to the power of this time, what is 2 to the power of 1? Okay. So I'm going to go plot the point 1, 2. Sure looks like it might be a parabola, huh? Okay, what happens when you raise 2 to the power of 0? It's 1. It's 1. Come to tutorials and we will talk about that. There's a really, yeah, I know you don't want to. We're not going to talk about it in here because it's a long explanation, but there's a reason for it. So if you want to know, you can come talk to me in tutorials and I'll explain why it's 1. Yes, that's an exponent rule from last year. So if you want to write it out to the side, anything to the power of 0 is always going to be 1. In fact, maybe I shouldn't put x. Maybe I should put like like a or something. That way it doesn't look like x is my base in an exponential function. So anything to the power of 0 is always going to be 1. So it's nice that you mentioned that, because if I have any base that's greater than 0 and not equal to 1, any base, if I raise it to the power of 0, what do I always get? 1. So what ordered pair will I always have unless I've done some kind of transformation? What ordered pair will always be on my exponential function? 0, 1. 0, 1 will always be in my exponential function as long as I'm not shifting this and doing some kind of transformation. So 0, 1, which also turns out to be the what? The y-intercept, which is nice that a common point on these exponential functions will be the y-intercept. We can say the y-intercept will be 0, 1. Okay, so that was one exponent rule that we needed to remember. Exponent rules from last year. So there's one of them. Huh? It might be. We don't know. Oh, you kept going and it wasn't a parabola? All right. Well, let's see what the rest of this looks like. So my base is still 2. My exponent is still whatever my x value is. So this time it's -1. Is it? Remember when you have like a to the power of negative something, n, what do you have to do with this? You have to put it under 1. Or if it's already under 1, you put it on top. But in this case, you put it under 1 and the exponent becomes positive. Remember? So is it going to be 2 or 1 over 2? It's going to be 1/2, because 1 over 2 to the power of 1 is just 1/2. You see that? So when I plot the point, I need to go to the left 1, but then only up like 1/2, which is going to be difficult with my pen that doesn't want to write. There. Oh, man. Ignore that. Okay. So what about if my base is 2 and my power is -2? What is this? That's not 4. 1 over. Man, there's a lot of guesses going on in here. 1 over 2 to the power of +2, which is 1 over 4. So -2, comma 1/4.
So if it's a negative exponent, it's going to be 1 over
something. Yes. Yes, it does. It's what, yes. So the denominator, so like this, 2 to the power of -3, is going to be 1 over whatever that positive exponent was. 2 to the power of 3 was 8, right? So this is 1 over 8. Yes. So if I graph -3, 1/8, again, with the fat pen, it's going to look like it touches the x-axis, but does it really? No, and so that's something that I want to talk about. We discussed it last year very briefly. It was kind of your first exposure to asymptotes. But here, every time you have a negative exponent, your y value is 1 over something. And as that something on the denominator gets bigger and bigger, what does this number get close to? 0, right? It gets really close to 0, but does it ever cross it? Does it ever turn negative? No, because it's always 1 over something. It also can never be 0 because 1 over something is not 0. The only way to get 0 is to put 0 over something. It has a horizontal asymptote. Oh my gosh. Absolutely. So take a moment to connect these, but you know that there is a horizontal asymptote here. So when you connect, be sure that your exponential function does not touch or cross y equals 0. I'm going to connect it with blue. There. Look how nice that looks. Okay. So with all parent functions, when we first start a new unit and we talk about the parent function, we talk about some key attributes, and there are like, I don't know, 7 or 8 that we're going to discuss. But I'm going to see if you, with all of your experience with asymptotes and exponential functions in the past, I'm going to see if you can fill them in. So don't write real big, because I told you there's 7 or 8 things that we're going to have to jot down. I'm going to need the domain. I'm going to need the range. I'm going to need the x-intercept. I'm going to need the y-intercept. What else am I going to need? Vertical asymptotes. Long word. Horizontal. What did you say you think the last one is? We talked about the asymptote, and there are no holes, so we're going to discuss end behavior. So as x goes to negative infinity, what happens? And as x goes to positive infinity, what happens? What is y doing? What's the pattern, the behavior? So I'm going to, maybe. I don't know. So I'm going to pause the video and I'm going to let you try and figure out what goes beside all of these things, what the domain and range and intercepts and asymptotes and end behavior are. You can do it alone or together if you want, but I do want you to discuss together at your group once you're all done, because I'm going to call on random people and I want you to have a little more confidence. So make sure you discuss with each other. Okay, so look at your answers. I'm going to call on some random people, but I'm going to tell you what I'm asking for first. So the first thing I need is the domain. Look and see what you put. Jasmine, what is the domain for this exponential parent function? All real numbers. Very nice. Okay. Next up, that's it. Why? Would there be something else? No. Let's see. Let's talk about, okay, so, bless you. Let's talk about why there's no x not equal to anything. That happened in rational functions, right? And that happened in rational functions because there were whats at certain x values. Holes, yes. Do we have any holes here? No. We do, but the only one that affects the domain would be a what asymptote? That is not true. If we had a vertical asymptote, that would affect the domain being defined at that x value. So, do I have a vertical asymptote?
But if b cannot equal 1, then why is it not?
B cannot equal 1, but that doesn't mean that x or y cannot equal 1. B is the base, remember? There is no vertical asymptote. So there is no place, and I'll have to erase this in a second, but like most people think, oh, there's a vertical asymptote right here. No, there's not. There's not a vertical asymptote right there, because if I were to continue this table, I'd continue picking x values, right? So if x were 4, 2 to the power of 4 is 16. And if x were 5, then 2 to the power of 5 would be 32. And if x were 6, and I could just keep going, right? Is there anything stopping me from picking x values of like 1,000, 1,000,000, infinity? No, the government, no. So there's no limit on the x values that I can pick, right? So is there any limit for how, I should probably use my pen, any limit for how far along the x-axis I can pick numbers? No. So is there a vertical asymptote? No. So are there any x values that are not defined in the domain? Not on an exponential. There are no vertical asymptotes for those exponential functions. But there is a horizontal asymptote, so look and see. I know we're skipping around, but look and see what you put for the horizontal asymptote, since that's what we're talking about. The horizontal asymptote, look and see what you have. Chris, what did you put for the horizontal asymptote? X equals 4? So x equals 1, 2, 3, 4. That would be like this. So it's not a horizontal asymptote. Horizontal would be this way. Y equals 0. Good save. Y equals 0. Remember that my values, as x decreases, my values are becoming smaller and smaller fractions, which means they're getting closer and closer to 0. So that's my horizontal asymptote. Okay. We skipped a bunch of stuff. Let's talk about range. I'll take a volunteer for the range. Range is tricky. Yes, ma'am. Is it what? Y equals 0 isn't the range because that's where the asymptote is. But it's all the y values that my function has. So all the y values that my function has are what, Mackenzie? Closer. All y values where y is not equal to 0. Here's y equals 0. So we know we can't have that. And I know I have y values being used up here, but do I have anything being used down here? No, the graph doesn't go down there because it's got this asymptote that's kind of repelling the graph. So you want to try, Adam? What's the range? Or was that what you were going to say? Oh, sorry. Okay, so let's think about like last year when we first did domain and range. If I were trying to go from the bottom to the top. Oh, what's the bottom? What's the bottom?
0.
What's the bottom? 0. What's the top?
All real numbers.
No.
Oh.
The top is infinity. Y is what? Say it again, Tabby. Not greater than or equal to, because where y is equal to 0, there's an asymptote. Y needs to be greater than 0. Well, that was a fun little dance around the answer. Yeah, y is greater than 0. It's not equal to 0. There's an asymptote there. It's not less than 0. There's no part of the function down here. It's just all the y values that are greater than 0. Okay, x-intercept. Look and see what you put. X-intercept, look and see what you put. Alex, what did you put for the x-intercept? I got none also. Good job. I think y'all are more comfortable with the idea that maybe there's no x-intercept or y-intercept or something like that. So that's nice. Y-intercept, look and see what you put. Evelyn, what did you put for the y-intercept? 0, 1. Question, is it ever going to be different? Yes? No?
No.
Oh, okay. So if it's shifting, yeah. If the graph is being shifted, yes. But if I'm not transforming my graph, no matter what my base is it going to be different? No, my y-intercept is always going to be 0, 1. Okay, let's talk about end behavior. As x approaches negative infinity, that means my x values are going this way. What's y doing? Getting really close to 0. Yeah. Y is approaching 0. As we go to the left of the graph, my graph is coming down, 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 and it's getting close to 0. So y gets close to 0. But it doesn't touch it, but it's trying to. And then as x approaches positive infinity, that's going to the right, correct? What's y doing? It's going to positive infinity as well. Very good. Nice, nice. Okay, let me go ahead and end this video.